What's up guys, this is Abhishek and in this video I'm gonna talk about how to use BJT, that is bipolar junction transistor, as a switch. Well, now before discussing it practically, I would like to explain it on the page, so let's get started. Well, but before discussing it, basically BJT operates in four regions, that is cutoff region, saturation region, active region, and breakdown region. But here we will focus on two regions, that is cutoff region and saturation region. So let's rock and roll. Well, number one, open switch. In cutoff region, BJT acts as an open switch. So basically what happens here, base emitter junction is not forward biased, that is IB is equal to 0. Well, this is a BJT having three terminals, that is base, collector, and emitter, right? Well, you can see that IB is equal to 0 because no input voltage is applied. So that's why IB is equal to 0, which means that IC is equal to 0. Even though there is VCC, but IC is still 0. So well, you can see that the switch, this transistor acts as an open switch. That is, ideally there is an open between collector and emitter. That is, you can see that collector and emitter, there is an open, and it acts as an open switch. So that's it. Well, number two, closed switch. Right, well, in saturation region, BJT acts as a closed switch. That is, base emitter junction is forward biased and base collector junction is also forward biased, right? Now, to understand this, well, this is a transistor, this is base, this collector, this emitter, right? Well, you can see here that IB is present because VBB is present. You know, we have applied VBB, and you know, there is IC, that is IC saturation, and VCC is also present, right? That's it. But you can see here the transistor acts as a closed switch. Well, ideally there is a short between collector and emitter. Well, you can see that in between collector and emitter there is a short. It means that current can flow here, right? And the saturation is, the current is IC saturation. That is, you know, the maximum current, and there is VCC also, which is applied voltage. Now we will understand this, okay? Well, now let's assume that we want to turn on and off an LED with the help of transistor, right? Well, this is LED, okay? And this is basically a common emitter configuration, right? And you know, I have to connect this LED to the collector terminal, right? Well, this is LED. Well, now let us first let us talk about this LED, okay? Well, the VLED is 2 volt, which means that we must apply 2 volt across this LED, and its ILED is equal to 20 milliampere, which is its rated current. That you know that 20 milliampere has to flow through this LED, and IC, so it means that IC is equal to 20 milliampere. But you know that ILED is equal to 20 milliampere. Then why IC is equal to 20 milliampere? This is because that as we connect this LED to the connector terminal, okay? And now for this LED, you know, to operate properly, we need 20 this amount of current, 20 milliampere, you know, the ILED. So this means that IC must be 20 milliampere. That's why IC is equal to 20 milliampere. And this is, you can see here, this is VBB, this is VCC, okay? And this is LED, this is transistor, and this, which is BC548B, okay, of this category, right? Well, now let us talk about this a bit more. And now here we can see that here, as we know that IC is equal to beta IB. But now what about IB? Well, IC is given, which is 20 milliampere, because this is the current which has to flow through the LED, and beta is also given. And for BC548B, the beta is 150, okay? And it means this implies that IB is equal to 0.133 milliampere, right? Now IB is this, okay, so it's okay. But what about this RB? What will be the value of RB, right? So now let's apply KVL. That is, VBB is equal to VB, which is this one, plus VBE, right? Well, you can say this VB is equal to VBB minus VBE. That is, and as we know that V is equal to IR, so that's why VB is equal to IBRB, which is equal to VBB minus VB, and that's now this we ends up with RB is equal to VBB minus VBE divided by IB. As we know that VBB is applied voltage, which is 5 volt. VBE is that volt for junction voltage, which is 0.7 volt, and for this is basically silicon, so that's why it is for junction voltage, which is 0.7 volt. and this is IB is equal to 0.133 milliampere. This is RB is equal to this one, okay, which is equal to 32.25 kilo ohm. So that's why we need RB of 32.25 kilo ohm. Right, but you can say that why do we need RB? Well, we need RB because I can't really apply this 5 volt directly across this base, because it will burn this transistor and something like that. Okay, so that's why we here we need to use RB, and this is how we find the value of RB. Right, so now let's talk about this practically. Okay, so well, this is transistor which is BC548B, and this is basically the collector terminal, this is base terminal, and this is emitter terminal. Okay, and this is LED. Right, well, this is the resistor which is connected to the base, and its value is 32.25 kilo ohm. But you can ask this question that why I have used 4 resistors. Well, basically 32.2 kilo 5 was not available, so that's why I connected 3 10k resistor and 1 2 resistor in series, and I get wrong about very close, that's very close to 32.25 kilo ohm. So that's it. Well, but you also can ask, you might this might come in your mind that why do I use this thing? Well, basically this is potentiometer, right? And why do I use this device? Well, because the applied voltage is 5 volt, right? And this LED, I have to apply only 2 volt across this LED. I can't really apply 5 volt across this LED. If I do so, this LED will burn. So that's why in order to get the 2 volt, I just use this potentiometer, and it gives me a value of 2 volt from that available 5 volt. So that's why I use this potentiometer. Now let us talk about how does it work, right? Well, you can see here this. Okay, well, this is when this IB here, IB is equal to 0. IB is equal to 0 because there is no input voltage, so that's why VBB is equal to 0. So this is the off state, and LED is not glowing, so it's off. Okay, and now when I apply VBB, this is basically VBB. Okay, this is VBB. Now you can see that the LED is glowing, and which means that the transistor is an on state, right? So this is how transistor works as a switch. Okay, like you can see here, off on, off on, off on. Well, like this is basically this is VCC. Sorry, this is yes, this is VCC, this is VBB, and this is basically base. This is this RB is connected to the base, and LED is connected to the collector, and that it's just think about this circuit, and you will understand this. This is basically this circuit, but it's a bit complicated, Well, so that's why now let us talk about it a bit more. Well, now let me. Well, what about this collector base emitter voltage? So well, VB is what? So VB is basically VBE is 0.7 volt. You can see this, which is VBE, and I have told you it is 0.7 volt, right? And this is VBC, which is 0.5 volt, right? Okay, and what about VCE, which is collector emitter voltage? So VCE is equal to 0.16 volt. Well, basically right now this is the transistor is in saturation mode, but as I have told you before here that base collector junction is 4 bias. How is it possible? Now so like I told you that this in case of closed switch, base collector junction is 4 bias, but how is it possible? Now so to understand this, let me show you something. Well, you can see here, okay, that's it. This is basically collector is equal to base. Well, you can see that the base VBE is equal to 0.7 volt, okay, and VCE is equal to 0.16. So it means that the base here it is 0.7. The base is more positive compared to collector. Well, base is P type and collector is N type, which means that base is more positive, mean that this base and collector junction is forward bias. Why is it forward bias? Why is it forward bias? Because the base is more positive compared to the collector. That's why base collector junction is forward bias in case of saturation. In case of saturation region. Thanks for watching.